Today we're going to be talking about two different cycloaddition reactions. In the Diels Alder reaction, a conjugated diene, 1, 2, 3, 4 diene, reacts with a dienophile to make a cyclohexene. If we number the diene, we can keep track of where the carbons go during the reaction. So in the diene, 1, 2, 3, 4 reacts with a dienophile, which is diene-loving, 1', 2', and if we follow the curved arrows shown, we create new bonds. We create a new sigma bond here in green, and a new pi bond between carbons 2 and 3. So our new bond is between carbons 1 on the diene and 1' on the dienophile, and 4 on the diene, 2' on the dienophile. And we have a new pi bond between carbons 2 and 3 on what was originally the diene. In general, Diels Alder products will have a cyclohexene structure in which you can identify the 2,3 position of the original diene by where the double bond is. Since this is a concerted reaction, meaning it happens in a single step, relative to the dienophile, we have to add in a syn manner. Also, the diene has to be arranged in what we call an S-cis. It looks sort of like the letter C prior to reaction, so that 1 and 1' are close enough to react at the same time that 4 and 2' can react. Finally, the approach of the diene to the dienophile is such that the same face of the diene at 1 will also react with number 4. Here's a orbital picture of what happens. Here's your dienophile, your alkene on the bottom, and here's your diene on the top, and we start getting overlap of the corresponding lobes. So one of the p lobes from the top alkene starts interacting with one of the p orbitals from the bottom alkene, like so. And that means that the diene plane that it's in and the alkene plane that it's in, we add syn relative to each of those planes. Now you might also notice that these lobes line up in a certain way. That is, that this dark lobe and dark lobe will overlap, giving a positive bond, and this light lobe and light lobe will overlap, giving a positive bond. This comes about because we are in fact overlapping the HOMO of the diene with the LUMO of the dienophile. That is, if you look at the 4 orbital pictures for butadiene back from the conjugation chapter, you'll find that the HOMO, the one that has a pair of electrons in it, has the symmetry shown. And that an alkene, LUMO, has the symmetry shown. And this turns out to be exactly the right symmetry for overlap and creation of 2 bonds at the same time. It also matches with our previous experience, in which we showed that a HOMO and a LUMO must overlap for a reaction to take place. In this case, the HOMO belongs to the electron-rich diene, and the LUMO belongs to the electron-accepting dienophile. One of the things we will talk about in this chapter is how to make that HOMO-LUMO gap in the yellow circle to be as small as possible. And it turns out if you can raise the energy of the HOMO and or lower the energy of the LUMO, that the HOMO-LUMO gap will become smaller. In general, the LUMO energy can be lowered by adding electron withdrawing groups, and the HOMO energy can be raised by adding electron donating groups. Now there's a lot of detail in the chapter on Diels Alder reactions, but there are only going to be a subset of these topics that I expect you to know. These include drawing curved arrow reaction mechanisms for the electrocyclic process, drawing a cyclohexene product if you're given the structure of the diene and the dienophile, drawing the diene and the dienophile if you're given the structure of the product. Realize that not all the dienes will only have 4 carbons. They will often have other groups attached, and the dienophiles won't normally just have 2 carbons, and therefore the product will have those corresponding substituted positions. In addition, we'll talk about factors which speed up a reaction, and that is those same factors that lower the energy of the LUMO and raise the energy of the HOMO, as well as the fundamentals of regio and stereoselectivity. For example, if I substitute specifically at the 2' position, does that end up actually attaching to 4 or to 1? We could flip this alkene upside down and it might also react. In general, those fundamentals of regioselectivity are due to electrostatics. The more delta positive, delta negative ends will react with each other. And finally, the stereoselectivity is related to syn. That is, relative to the alkene, both new bonds are made on the same face, and relative to the diene in the cis configuration bond, both new bonds are made from the same face. The second major topic of the chapter is oxidative cycloaddition. And we've actually seen one oxidative cycloaddition reaction in the past, and that is the formation of an epoxide. The peroxy acid delivers one oxygen atom, making two bonds at the same time. And even though we can't see it on the substrate shown, the propene that we started with, both of these bonds were made from the same side, syn, because they were made at the same time. Much like we had to do syn cycloaddition in making two bonds in the Diels Alder. Recall that one of the interesting things we could do with epoxides once we'd formed them is form a new bond at one of the two carbon atoms through an SN2-like reaction. That is, if we specifically use either acid and water or base and water, we would end up doing an SN2-like reaction at one of the two carbon centers, and we'd end up with a diol. But overall, those OHs would have been added from opposite faces because the second one comes in from the opposite side. In this chapter, we introduce a different oxidative cycloaddition reaction using either cold KMnO4, like you've used for functional group tests to test for alkenes, purple to brown precipitate, or we can also accomplish our cycloaddition using osmium tetroxide followed by a reducing agent. Either one of those ends up giving you an OH on adjacent carbon atoms in a syn fashion. And the reason that they end up syn or cis to each other is because the intermediate of the cycloaddition reaction, where the metal in the center here is either manganese or osmium, depending on whether you started out with the KMnO4 or osmium tetroxide, the intermediate is made in a single step, a single cyclic step. And that allows us to do syn addition. Once the metal is cleaved off, we end up with our diol. 1,2-diols can do further oxidation reactions in which they oxidatively cleave the bond, the sigma carbon-carbon sigma bond between the two OHs. This is most often accomplished with the periodic acid, and the resulting compound has a C double bond O on each end of what used to be the CC carbon bond. Any H's or carbons already attached to that bond are maintained. So in the end, you end up with aldehydes and or ketone products. In this chapter, we are also introduced to a reagent that can directly cleave a CC pi bond into the two component carbonyl parts, and that is ozone. This is the same ozone in our atmosphere that's bad for our health but good for absorbing UV radiation. And if we treat an alkene with ozone, it undergoes an initial cycloaddition, a rearrangement, and then a reduction with reagents that we add in a second step to give you identical cleavage products to that which you get from cleaving the diol. That is, the CC pi bond is broken, and each carbon on the end replaces that C double bond C with a C double bond O. Finally, we're provided with one additional way to do an oxidative cleavage with a much stronger oxidizing agent. This is the same potassium permanganate that when we used it cold and basic gave us a diol. If we use that same reagent and we do it hot in the presence of acid, we will not only cleave the double bond, just like the ozone or the periodic acid does, but we will also oxidize any CHs attached to those carbons being oxidized. So for example, if you start off with a C double bond C, that will become a C double bond O, and each of the H's on that same carbon atom get oxidized. Notice that KMnO4 leaves any carbon-carbon bonds alone. Finally, you might ask, why would we want to chew up organic materials? We've spent a lot of time in the course learning how to make carbon-carbon bonds. What value is there in cleaving carbon-carbon bonds? Well, it turns out that cleaving carbon-carbon bonds is one of the chemical tools we have to identify the structure. If we have a structure for which we cannot otherwise determine, but it has CC pi bonds in it, we can selectively oxidize those CC pi bonds and then analyze the fragments for something that we can positively identify them at. For example, we could say we had a compound, and when it was treated with ozone followed by zinc, it made formaldehyde and ethanol. Then you could imagine taking this formaldehyde and ethanol, cutting the oxygens off, putting the carbons back together, and deduce the original structure of propene.